Today I want us to look at the derivative of exponential functions. Of course, now we are in a position whereby we have already exhausted so many different possibilities and so many different techniques of finding derivatives, but now we have not covered the derivative of exponential function. It doesn't mean that you can't. In matter of fact, I would say this: try and solve these exponential find the derivative of these exponential functions and see what you are getting. But if you are not getting anywhere, you can proceed with the video. But if you think you can try, and then after trying, if you get stuck, then you can proceed with the video. And also another thing that is also more important here, I want you to notice something: that you have already invested a lot to actually be at this position in the semester, and it wouldn't be wise to give up now because you are almost there. If I'm not mistaken, we are left about, I think, less than 11 topics to cover, which means that you can still hang in there and make sure that you practice as much as you can for the following tests and also the exams. Yes, here one thing that I want us to take note of is that I want us to solve these problems here. You will see they're not that hard, they are easy. At this side here we have exponential functions and some manipulation there, because this is not an exponential function but it is some kind of an exponential function. And this side here we have logarithmic functions and a mix of some functions. So I want us to see if we can get these things here. So the first one is saying that we wanted to find the derivative of this function f of x is equal to e of x. Of course, we have dealt with the power functions, whereby we said a power function is a function of this type and its derivative is going to be f prime of x, and then you bring this n down and then you multiply by x and you raise n minus 1. And if you notice the power functions, the independent variable x is actually the base. But if you are looking into this here, this is not the base here, is not the independent variable, it is actually a constant. So there is no way that you can end up saying that the derivative of this function is going to be you bring down x and then you subtract a 1. This is actually not correct at all, because this is not a power function. So in this particular case, we cannot use the power function or the power rule of derivatives. And here we don't have any sum here, so we cannot use the sum rule. And we can see that there is no minus here. We're not subtracting functions here, so we cannot use the difference rule. And then fourthly, there is no multiplication of two functions here, so we cannot use the product rule. And there is no division of two functions here, we cannot use the quotient rule. And more importantly, when it comes to this, we don't have a function sitting inside another function here, so we can't say we're gonna use the chain rule. So most of these techniques that we have actually covered cannot solve this whole thing, and now we're only left with one thing, which is actually using the first principle of derivative to find the derivative of this function. And the first principle is saying that this is supposed to be h plus x minus f of x, and then you divide this whole thing by h. And then if you notice here, the limit, we always have the limit as it is, and then in the value of x here we're gonna plug in this whole thing and end up having e raised to x plus h, and then minus f of x. We take the function as it is, so we have e to the power x, and then you divide this whole thing by h. Of course, the limit is always kept there, and we only drop it when we are actually evaluating. So here, this whole thing here, we always say that whenever I have a to the power n and I'm multiplying a to the power m, I have two bases. I have two powers of the same base and I'm multiplying them. I always keep one base and add the exponents. So if I have two exponents being added, I can split the bases and have these different exponents. So I wanted to change this to be in this form here. So I end up having e is the base. So I'm going to take one exponent and then I multiply by e raised to h minus e to the power x. You can see how easy this thing is. And you can notice something here, that if I were to take this h and plug it here, I will end up having e to the power 0, and e to the power 0 is just 1 because e is a constant. 1 times e to the power x is going to be e to the power x. E to the power x minus e to the power x is going to be 0, and then I'm plugging a 0 here. I'll end up having a 0 over 0. So one way to deal with a limit of that kind is to factorize and see if you can cancel out something. So I am going to factorize. I have e to the power x and e to the power x, so it is common. Once I take it out here, this one is gone. I will be left with e to the power h minus, and then this one I will end up having a 1, and then I divide this whole thing by h. But if you notice here, even though I factored out that's e to the power x, it's not cancelling out with anything. So because it's not cancelling anything, I have to try another way of dealing with limits, which means that let's first deal with this whole thing here. If I have multiplication of two things, then the denominator can either go with e to the power x, or it can go with e to the power h minus 1. So I choose to place it here because I know that the limit of this whole thing will exist, and I know the limit of this will exist. So if that thing of cancelling is not working, I'm going to try rules for limits. Rules of limits are saying that if you have a product of two functions, you can just take the limit of the first function and then take the limit of the second function separately, and then if this limit you get them or they exist, and then you can multiply them, you will get your answer. But if this limit does not exist, or this one does not exist, we cannot use that rule there of splitting the limits. We only use it when the limit exists. If this limit does not exist, it does not mean that this whole limit cannot exist. It just means that we cannot use that rule. We need to try another method. So here I can see that there is no h here. Because there is no h here at all, what we actually need to do here, we need to notice that this part here is a constant when we are actually considering h, because there is no h here. So this is a constant. So the limit of a constant is always going to be that constant. And then if you look into this limit here, I want you to remember that when we're using the squeeze theorem, we said that if I have x and then I have x minus 1 over x, this limit is always equal to 1. I'm not sure if you still remember that when we're actually saying that e to the power x can actually be bounded by x plus 1, and then x times e to the power x plus 1. We had this inequality that actually helped us to actually prove this whole thing. Others also provided that you can either use this inequality less than or equal to x squared plus x plus 1, and the other one was 1 over something here. So we had so many variety of functions, and we used the squeeze theorem to prove this. So I have x here, I have x here, and I have x. So if that is the case, then this is supposed to be 1. So if I change this x to h, I have to change this one also to h, and I have to change that one also to h. It has to be the same as 1 because h is still the term variable. I have the same thing here, so this whole thing is supposed to be equal to 1 or e to the power x. The meaning of this whole thing is just saying that if you take the derivative with respect to x of e to the power x, you're supposed to get the same thing. That's what this thing is actually saying. That's actually nice, because if I have that, I know that I can also find the derivative of this function here with e to the power x. And if you remember, when we're dealing with the laws of logarithms, and also you still remember the change of bases, we said that the first one was if I have log a of x times y, this is the same as log a of x plus log a of y. And if I have log a of x over y, this is the same as log a of x minus log a of y. And then if I have log base a of x to the power b, I can always bring this down and have b log base a of x. And if I actually end up having log base a of x, this is the same as saying I have log base b of x divided by log base b of a. I hope you still remember these things, because this one actually helped us to conclude that log of a, as long as this number and that number is the same, we know that this is always going to be equal to 1. That's what was important here, that we came out of this. And then we also concluded some other things that were so much important here, that if I have a to the power x, this is always going to be the same as b raised to log b of a to the power x. This one is when we're change of bases. And also this same thing here, if you have a to the power x, this can also be the same as log base b of b raised to a to the power x. So we can always have something of this nature here. Take note that this whole thing is an exponent of b. So if you bring it down, I have b and b, so it's going to be 1. I get the same thing. So these are the things that I want you to remember in this particular lesson, which means now we will end up having this function is the same as e. Why am I changing this to e? Is because I already know the derivative of e. So I have e raised to log base e. Take note that this base here must be the same as that. So since I have a e, I must have an e there, and then I will end up having a to the power x. And this is the same as e raised to using this rule here, that if I have an exponent, I can always bring it in front of the log. So I'm gonna bring this x down, so I end up having x times log e of a. Or someone might say, because we have let me leave it like that for now. Let me leave it like that. And now that I actually have this nice thing here, I know how to take the derivative of a function h of x is equal to e to the power x, because h prime of x is still going to be the same thing. That's what we actually found above here. So because I know that this whole thing is going to happen, but now the issue that I have, instead of having e to the power x, this is x, I have another thing that is sitting in this place of x here. So I have something that is sitting there. So because I have something sitting there, I am going to let that thing here to be u. So I'm going to let u equal to x times log e of a. And then after I've let that end, my y now is going to be actually I'm going to replace this whole thing by u, because this is the same as u. It's going to be e raised to u. And then what I'm actually looking for, which is the derivative, is the same as dy dx, but now my y is in terms of u, so I cannot take the derivative with respect to x. So I need to change it and say I have dy du, because this is written in terms of u, and now I have to multiply by du, because this du was not part of that, and then I take du with respect to actually x, because actually my u is in terms of x here. Now that I've noticed something here, because this is a constant, this is a constant, so this whole thing here, log e of something, is a constant. I want you to take note of that. And then here I'm gonna take d du, so I have d du, and then instead of y, my y is e raised to u, and then I multiply this by d dx, and my u is the same as x times log e of a. And then I can proceed here and say that what is actually the derivative of e to the power u. I know that the derivative of e to the power u, as long as I have u here, if I had x and x, I was still going to get e to the power x, but now I have u and u, so I'm still going to get e to the power u. So the derivative of this is going still to be the same thing if I have this. I have u, and this number here is an e. And then when it comes to this here, I want you to note that this is a constant, this is a constant, so this whole part here is a constant. So when you are taking the derivative of a function times a constant, I can always just pull the constant first out and then take the derivative of what remains, which is this x here. And then if you take a look into this, this is going to be e raised to u and then times log e of a, and then I'm gonna times this. What is the derivative with respect to x of x? There is a 1 there. I can just bring in the 1 and then multiply by the independent variable x, and then I have a 1 which was there, and then I'm subtracting a 1. 1 minus 1, we know that it is a 0, and then x to the power 0, we know that it is just a 1, and 1 times 1 is a 1. So the derivative of x with respect to x is just a 1. And then if I multiply this whole thing, I will end up getting u e to the power u times log e of a. And then if you look into this, now I need to replace this u because I did not have u in the original equation. So my u is x times log e of a. So here, this is going to be e raised to x log e of a times log e of a. And of course here, if you notice here, whenever I have something in front of a logarithmic function, I can always take it and make it the exponent of what was inside to get something of this nature here. So if you look into this here, this is going to be e raised to log e of a to the power x times log base e of a. And we can proceed here and notice that I have log e and e. Those two things, they cancel out, and now you are left with a to the power x times log e of a. Therefore, one person can conclude now that the derivative with respect to x of a to the power x is always going to be a to the power x times log e of a, or just log e means ln of a. So when someone is saying this, they are still within their right, they are right. Or someone may say a to the power x log base e of a. And another thing that I want you to notice now is this thing here. If we were to change this and we're looking for the derivative with respect to x of, instead of a, I'm going to place in e to the power x, right? And now I'm gonna use this formula here. You will find out actually that this constant can be any constant as long as it is bigger than 0, and then this is a constant. So this whole thing is going to be e raised to x, and then ln of that constant that we had. We just place an e there, and we know that ln of e is just 1. That is why we end up having something of this nature for this one. So the derivative of this is that same thing, but in generally this is how this is actually going, because we found that. I was just trying to verify this formula with e here, if a is e. So whenever you are looking for the derivative of some constant raised to an independent variable, this is how you actually go about it. Let's go now to the third one. I have my f of x is equal to 5 raised to x. I want f prime of x. This one is easy because all I need to do, take this as it is. I have this x here, and then I multiply by ln of this constant, ln of 5. That's how easy this is, because we already found the formula to find the derivative of an exponential function. It is like this. So clean, we're fine. Let's go to D. Our D is saying that we want the derivative of f of x is equal to 5 raised to sine of x. one thing that I know for sure is that if I have h of x is equal to 5 raised to x, I know its derivative, because its derivative is going to be 5 raised to x times ln of 5. But instead of having an x here now, I have something else. So there is something that is sitting in the value of x here. And that something here, we were supposed to have x, and I was going to just take a derivative right away. But now I don't have an x here, I have a sine of x. So to deal with this whole thing, what is sitting in the value of x, I'm going to let it to be a u, so that I can get something easier. So I'm going to say let u equal to what was sitting in the value of x, sine of x. And now my y is going to be a new function, still the same function, 5 raised to, but instead of having this whole thing, I'm having a u. So that's how this thing is actually happening. And then now the derivative, f prime of x is going to be the same as dy dx. But here my y is in terms of u, so I cannot take it with respect to x. So I have to take the derivative with respect to u first, and then take the derivative of u with respect to x. I will be able to get that whole thing here. And then I still have d du, but instead of y, I know actually my y is 5 raised to u times d dx. And then if you look at my u is the same as sine of x. What is nice now is that this function is in terms of x, and I'm taking a derivative with respect to x, and this function is in terms of u, and I'm taking the derivative with respect to u. So everything is going to be fine. What is the derivative of this? The derivative of an exponential function where this number here is not in e, is always going to be the same thing. And now I take the ln of that constant, so I have a 5 there. And then the derivative of sine, we know that is going to be cosine of x. And then the next thing that I need to do here, I need to replace this u by sine of x. So we're actually having 5 raised to sine of x times ln of 5 times cosine of x. So this is actually the derivative we're looking for. Technically speaking, here we're taking the derivative of 5 raised to something, so it's going to be still the same thing, and then we take ln of the constant, and then we take the derivative of that something, which is cosine of x. That's how easy this thing is. Now let's go to e, and e is saying that find the derivative of f of x, which is the same as 3 raised to 2x times cosine of x squared. So what I want you to notice here is something that is so much important here. When I am actually, if this function was h of x, it was equal to 3 to the power x, it was going to be easy, because my h prime of x was just going to be 3 raised to x times ln of 3, and we're going to be fine. But now, instead of having just an x here, I have something that is sitting in the value of x, and that is the something that we are talking about here. So I am going to let my u to be that something. So my u is going to be that something there. I'm going to say let u to be equal to the something, which is 2x times cosine of x squared. And then if you look into this here, we can actually also say that our y is going to be this whole function 3, but instead of having that whole thing, I know that whole thing is just going to be a u. And then now my f prime of x is going to be easy, because my f prime of x is going to be dy dx, but my y is in terms of u. That is why now I have to take the derivative with respect to u, and then take the derivative of u with respect to x. And of course you can see that I have du, and then my y is going to be 3u, and then times d dx. And then now my u is going to be 2x times cosine of x squared. And then of course you can see that we're actually having something little bit nicer here, that I have a u and a u, so the derivative of this is always going to be 3 to the power u times ln of this constant here. And then this part here, I have this function here and is multiplied by that function there, so I have to end up using the product rule because I have two functions being multiplied together. So I'm going to open some big brackets here. So I keep the second as it is, cosine of x squared, and then I multiply by the derivative of the first, which is just 2x, and then plus I keep the first, which is 2x, and I multiply by the derivative of the second, which is cosine of x squared. And then of course here I know that what was my u? My u was just 2x cosine of x squared, so this whole thing here is going to be 3 raised to 2x cosine of x squared, and then times this ln of 3 here. This is just ln of 3, and then inside here I still have cosine of x squared, and then this whole thing, what is the derivative of this whole thing? We can always pull out the constant and take the derivative of this whole thing here, so we end up times dx of x. So x is the same as x to the power 1, and then plus 2x times dx of cosine of x squared. I'm not doing anything here. We'll let you know later why am I not doing anything. So this whole thing here is going to be 3 raised to 2x times cosine of x squared times ln of 3, and then inside here we know, using the power function, we can always know that this one you bring the exponent down and then you subtract a 1 there, and then 1 minus 1 is going to be 0. X raised to 1 minus x raised to 0 is just a 1, so we will end up having a 1 here as a derivative. So this whole thing is going to be just 2 times cosine of x squared times the derivative of this, which is just 1, or dx divided by dx is just a 1. So I'm not gonna place a 1 here, so it's just a 1. So I'm just gonna remove this one here and live with that, and then plus 2x times the derivative with respect to x of cosine of x squared. Now we are only left by with just finding the derivative of this whole thing here. How do we end up finding the derivative, or this derivative? I'm gonna start writing here. We know that this is supposed to be equal to, I'm still going to have 3 times cosine 2x cosine of x squared, and then I have ln of 3, and then inside, of course, I'm still going to have 2 times cosine of x squared, and then I'm going to have this part here is going to be 2x times whatever I'm going to get here. Let me just put some brackets and be ready. So what I'm trying to find here, I am actually trying to find the derivative with respect to x of cosine of x squared. So I know how to find the derivative of cosine of x, right? And I know that the derivative of cosine of x is just going to be minus sine of x. I know that. But now, instead of having this x here, I am actually having something else. There is something that is sitting there. So how do I end up finding the derivative of this whole thing here? So what I'm going to do here, I'm going to let u equal to that something that is sitting inside here, which is going to be an x squared, and my y is just going to be I'm going to replace that whole thing by u, so I'm going to just have cosine of u. And then now that I have this whole thing, so our dx of cosine of x squared is going to be the same as dy dx, and my dy is in terms of u. That is why now I have to take the derivative of y with respect to u, and then take the derivative of u with respect to x. And taking a look into this, I still have du of this thing here. I mean, this my y here is that thing here. So I have cosine of u, and then I have dx, and then my u is just an x squared. So here I end up having, I have a u and a u. So the derivative of cosine of u with respect to u is going to be minus sine of u, and then here the derivative with respect to x of x squared, I'm going to bring down the 2 and then multiply by the variable and then subtract a 1. So it's going to be just 2x, or just minus 2x times sine of u, and my u was x squared. So that's how this thing is actually happening. So this derivative is just going to be minus 2x sine of x squared. So here this derivative is just minus 2x sine of x squared, and then I can simplify further and just say I have 3 raised to 2x cosine of x squared, and then I have a ln of 3 here, and then inside, of course, I am going to have 2 cosine of x squared, and then minus and a positive. If I'm multiplying positive and a negative, I'm going to get a negative. 2 times 2 is going to be 4. X times x is going to be x squared, and I have this sine of x squared. So that's how you end up finding this nice derivative here. Now let's go to the last 5 questions. We wanted to find this was actually our A. So we wanted to find the derivative of this. So we have plus y cube is equal to 6xy. So that was the first thing here. So what I want you to notice here is that we always had y is equal to something, or f of x is equal to something. But now in this particular function here, we cannot isolate y and make y the subject of the formula. Now, when we're actually having a function of this type whereby we cannot isolate y and make it the subject of the formula, we use what we usually call implicit differentiation, right? So implicit differentiation, what this simply means that because we are looking for dy dx here, we're just gonna take the derivative with respect to x, because this function and that function is the same. So I'm going to take the derivative of what of the left hand side, and then I'm going to set this equal to the derivative of the right hand side. That's what implicit differentiation is saying. Just take the derivative on both sides. You don't have to worry about making y the subject of your formula. Just take take the derivative on both sides with respect to x, because we were actually looking for dy dx, so we have to take the derivative with respect to x. And now it's easy to just proceed here, but before we can go and start making mistakes here, I want you to notice that y here is the same as f of x. Of course, this y here is the same as f of x, and of course, because we have y cube here, this simply means that I have f of x raised cube, and then here I just have f of x. Now, one thing that I know of here is something that is actually nice. I want you to keep this in mind, that I know how to take the derivative of some function h of x is equal to x cube. Right, I know how to take that. But in this case here, if you look into this, I am actually having a function f of x, and this function is raised to 3. So this y is f of x is raised to 3. So what I'm actually going to do here, I want you to notice something that I'm about to do here is that I am actually going to let my u to be equal to that function that is sitting inside, which is that y there. I'm going to say that my u is going to be my f of x, or I can just say it is a y. So that's what I want you to realize here. And if you have this u here, I also need to be able to notice something, that if I change this now, instead of having this, because I have this function that is sitting inside, I want you to notice that every single time, so if I am looking for f prime of x, my f prime of x is not going to be dy dx anymore. It's going to be dy with respect to u first, and then we take du, and then we take it with respect to x at a later stage. But this y here is actually going to be the new function that we actually have. So we're supposed to have our function y here equal to something here, but now we can't isolate y as a subject of the formula, so this one is not even significant anymore. But bear in mind that this is actually what we are actually trying to use here, which is the chain rule. So bear in mind that this is what is happening. So this whole thing here, I can say that it is going to be the same thing as it's going to be the same thing as let me first clean this whole thing up. This whole thing here is going to be the same as, I'm going to take the derivative with respect to x of x cube, and then plus I'm going to take the derivative with respect to x of y cube, and then on the right hand side I also want you to notice something here, that I have this function here, and I also this function here f of x, and they are multiplied together. So when we are having two functions, you just end up using the product rule to get that. The product rule is saying that keep the second, and then take the derivative with respect to x of the first, which is 6x, and then you add, and then you keep the first, which is 6x, and you take the derivative with respect to x of the second. So that is basically what is actually happening here. Now, one thing that I want you to notice here is something that I want you to realize here. This y here, we know that our y here was a function, so that function we letted it to be a u. So this one I'm going to use a u here, and then if you look into this y here, I am going to use a u instead, because our u was that function f of x. I hope you can get the what I'm trying to do here, that this y here is actually a u because it was a function. So now if you take a look into this thing here, I have this and that they matches out. So I have x, I am going to end up having I'm going to actually end up having this is x and this is x, so these two match up. So the derivative of this is actually the derivative of a power function, so I have to bring that down the 3, and then I have an x, and then I subtract a 1 in the exponent, so I'll end up having a 2, and that's it. Plus, and then when it comes to this one here is a u, and here I have an x, so I want to be able to actually take the derivative of this thing. How can I actually do that? I want to take a derivative with respect to u, so I am going to take du so that I can take the derivative with respect to u here. So I will end up having our u cube. But now, because I have this u, which was not part of this, I still have to take the derivative of this, of u with respect to x here. I hope this makes a lot of sense here. And still here I have a u, and then dx of 6x, and then plus 6x, and I still have dx of u. Right. So if you take a note here, is this here I'm still going to have 3x squared, and then here I'm taking the derivative of this with respect to u. Because this matches out, I will end up having, I bring the 3 down, I have a u, and then I subtract a 1 there, I will end up having a 2, and then this one is done. Now I'm left with this, which is just du dx. And then if you look into this, I still have a u, and then the derivative of 6x with respect to x, we know that is just going to be a 6 here, because there is a 1 there. When I'm bringing in a 1, it's going to multiply with this 6, and I'm left with a 6. When I'm subtracting a 1 there, I will have a 0. X to the power 0 is just 1. So that's what we are left with a 6. And then plus, and then here I still have 6x, and then this part here is going to be, I'm taking the derivative of u with respect to x. I don't know what the value of u is, so I leave it as du dx. Now that I have this, everything that have that actually have a du, I want it to be in one side and everything on the other side. So I have 3u squared du divided by dx. I take this and it jumps the equal sign, so it's going to change its sign to be negative. So I end up having 6x, and then I have du dx. And then on the other side, this one was just 6u, and then this one is jumping the equal sign side, so it's going to change it to be 3x squared. And then I factorize du this side, so I'll end up having du and dx. And then here I will end up having 3u squared, and then I'm going to subtract 6x, and then on the other side, because if I'm taking this du, I will be left with that. If I'm taking this du dx, I'll be left with this minus 6. And then this side I still have 6u minus 3x squared, and then of course I divide on both sides by this, and I will be left with the du dx, which is the same as 6u minus 3x squared, and then I divide this whole thing by 3u squared minus 6x. And we can go back now and realize what was actually our u. So we chose our u to be f of x, and this f of x is the same as y. So everything that is u, I'm going to replace it by y because I had a y there. So I have a u here, which means now therefore our dy dx, so I'm replacing this u by y, is equal to 6 times y minus 3x squared, and then divided by 3y squared minus 6x. So that is actually the derivative we were looking for the first one. So just a quick recap here. You just take a derivative on the left and the derivative on the right, and then here when you are having this y, you must understand it is the same as f of x, and you let your u to be that f of x, in other words it is that y. And then this side, you can realize that we have two functions being multiplied together, which means that you have a product, two functions, or you can actually start using the product rule. And then on the left, you can take the derivative of this, but when you're taking the derivative of this, you need to realize that our y is actually a u, and this u and x, they don't match out. That is why you end up having to take the derivative of u with respect to u, and then take because this u was not part of this, so you end up taking the derivative of u with respect to x. Kind of something like you are cancelling this one with that, right? And then you do the same thing on the right hand side, and then you can proceed all the way down. But you have to remember that your u was actually y, and we're looking for dy. So every time you have a u, you replace it with y, and then you are actually cool and you're good to go. And then the second one, which was actually a b was saying that you have y, and y is equal to cosine of xy. Again here, I want you to realize that this is the same as f of x, and then inside here, looking into this part here, I want you to realize that this one is actually f of x, this y here. And now that you actually have something also that you actually need to notice here, I want you to notice there are so many things that are happening here. This is just f of x, and I know if this function was something like I have h of x is equal to cosine of x, I know the derivative of this, that it will be h of x, and h of x was just going to be minus sine of x. I know that. Or the derivative, of course, is that. But now, instead of actually having cosine of x. Here I have something, so I have this something here. So what I'm actually going to do here, I want you to notice something, that I am actually having something that is nice here sitting in here. So I am going to let my u to be whatever is sitting inside there. So I'm going to let my u to be equal to x times a y. And now that you're actually having this thing here, I want you to also notice that now this function here, I'm going to now have a new function v, and this new function is going to be equal to cosine of u. That's what I want you to realize. So this whole thing here, I am actually going to replace it by u. The reason I'm not using y like I used to when I was actually doing chain rule is because I already have a y. I don't want to confuse these two things. Now, I want us to actually notice also something here. So basically here, I have this u here is a function x times f of x. If you notice here, this u is this function here, x times f of x. So that's what I want you to realize. This is f of x and this is f of x, but this is sitting inside. I'm going to let it u, and then change this whole function and call it v, and then I have cosine of u. Then my dy dx, which is this function here, is actually going to be the same as, I wanted to end up having my dy, and now I want to take this with respect to u first, right? So that's what I want to actually do, and then later I am going to take du with respect what am I doing now? Okay, I changed this one because I want dy dx. This is just, sorry for the confusion here. I wanted to take dy, which is this one here. So this part here is not going to be it's not going to, we're not going to be using these y's here. I am first going to take this v here, not a y. So I'm going to take dv with respect to u first, which is that u, and then later I am going to take the derivative of this u with respect to x, because I've changed this y to be in terms of v, so I have to take this like this. And then secondly, if you notice this, I still have dy dx on the left hand side, and then I am taking this part here, right? Now, if I want to take the derivative of this whole thing, I'm still going to have du of v. My v is supposed to be cosine of u. Can you note that now I have a u and a u, which is something that is nice. And then I'm going to take the derivative with respect to x of actually u. My u is actually x times y, which is something that is actually nice also. This one is still going to be dy dx, and then if you look into this, what is the derivative of cosine? Take note that we have a u and a u, so I'm going to take the derivative of cosine. The derivative of cosine is going to be minus a sine of u. That's what is nice. And then here I still have dx, and then inside here I am going to end up having x and y. I'm not going to deal with this now. First I need to substitute there. I have my dy, I have my dx, and then here I have minus sine of my u. What was my u? My u was x times y, so here I end up having x times a y. Now let me keep this one as it is and explain what is about to happen here, because I have x times a y. I told you that this one here is just a function f of x. So if you look carefully into this here, I have this function times another function, because this one is a function with respect to x. So if I wanted to take the derivative of this thing here, I have to realize that I have a product of two functions. One function is y is equal to x, and the other function is just f of x, which is this y here. So this whole thing is going to say I have dy dx on the left, and then on the right hand side I still have minus sine of xy, and then in this particular case here I'm going to open some brackets, keep the second as it is, and then take the derivative with respect to x of the first, and then plus keep the first as it is, take the derivative with respect to x of the second. I want you to take note of this because this one was actually a function on its own. So we take the derivative of this, and then we take the derivative of that. And now that we can see that, we can actually see that we have dy, and then you have dx this side, and then here you end up having minus sine of xy, and then in this particular case here we have something nice here. I still have my y, which is a function f of x, and then this one here, what is the derivative of x with respect to x? We know that it is just a 1. The derivative of x, we know it is just a 1. Or if you want to interpret it differently, I have this function y is equal to x. What is the slope of this function? We know that the gradient is just 1, which is that number that is in front of that. So it's just a 1, and then plus x times dy dx, because we don't know what y is because we can't make y the subject of the formula. And then we can say that we have dy dx, and on the right hand side I have minus sine of xy times this y here. So I have a y there, and then if I multiply this with that, I will end up having minus sine of xy times x times dy dx. So I have dy dx this side, I have dy dx on that side. I want to actually take this to the left hand side, so I am going to end up having dy dx. This one was negative, so it's going to be positive this side, so I end up having sine of xy times x dy dx is equal to, and then I leave this as it is, so I end up having minus y times sine of xy. This y is this one, and then I factor out dy dx here, and then after factoring dy dx I will be left with if I take this dy dx I will be left with 1, and then I take this dy dx, I will end up having x times sine of xy, and then on the right hand side I have minus y sine of xy, and then I divide on both sides by that thing, and then I'm left with dy dx, which is the same as minus y sine of xy, and then I'm dividing this whole thing by 1 plus x sine of xy. So this is actually the derivative that we're looking for, or the slope of the tangent line that is touching the given curve at point x. So this is actually the derivative that we were actually looking for. Just a quick recap here is that we actually had let me just make it here so that it's quick. We actually had y is equal to cosine of xy. So in order for us to find dy, we just take the derivative on both sides with respect to x. So we take the derivative of this, so we end up have dy, and then on the right hand side we still also take the derivative with respect to x of cosine of xy. That's just a quick recap. And this one we kept it as it is. We had this dx, and then when it came to this one here, we take the derivative of the outside, and derivative of course is going to be minus sine, and we keep what is inside as it is, and then we multiplied by the derivative of what was inside, which was xy, and then of course this side we had this dy dx, and then on here as long as I still have this sine of xy, we're still fine. And then I started to take the derivative of what is inside, and I saw that this is a product. You keep the second, and then you take the derivative of the first, and the derivative of x is just 1. And then we ended up saying, now I'm going to add, and then I keep the first, and then I take the derivative of the second. I'm going to take the derivative of the second, which is just going to be our dy dx. That's what was actually happening here. And then after that, I realized that actually I have this dy here dx, I have that dy dx, and I want to combine them. How do I actually do such a thing? I can see that, what I can actually do here is very easy. I can just decide I am going to just either divide this whole thing, that side, and then be left with this, or just simplify this as minus y sine of xy, this one here, and then minus x times sine of xy times dy dx. And then of course I take this to the other side, and I ended up having your dy dx minus, because it was minus, became a positive, x times sine of xy, and then we had a dy dx is equal to minus y sine of xy. And then after having something of this particular nature here, we ended up saying that I can factorize here, and then after factorizing I ended up having dy dx is just equal to y minus y sine of xy, and then I divided this by whatever was inside, which was just 1 plus blah 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 blah. Hope you understood this whole thing, because this is how the implicit differentiation is actually working. Now let's take another couple of examples. These couple of examples now are much more interesting than anything we have done. C was saying we had our f of x, and our f of x was equal to log a of x. So how do you end up taking this? One thing that I wanted us to notice here is that f of x is the same as y is equal to log a of x. And if I were to make x the subject of the formula, I know that this is actually the same thing. They mean the same thing. We have exponent is equal to log base the number. So I have a number x here is equal to a raised to an exponent. So this and that, they mean the same thing. So if I have x is equal to a raised to y, and I want to find the derivative with respect to x, all I need to do, I need to take the derivative with respect to x of the left hand side, and then take the derivative with respect to x of the right hand side. That's what is important here. And if you notice here, this y here is a function f of x, right? We have a function f of x. What is actually the derivative of this whole thing here? The derivative of x with respect to x, we know that is just a 1. And then the derivative of this whole thing here, we don't know it yet, but we're about to find out. So I have a raised to y. And we said that this y here, we know that our y is the same as f of x. So this f of x, because it is a function, and because it is a function, I know that I can find, if I had a function, let's say f of h of x is equal to a to the power x, I know how to find the derivative of this, because the derivative of this is going to be the same thing as it is times ln of that constant. But now instead I have y, which is the same as f of x there. So I have a function that is sitting in the value of x. So how do I end up dealing with that? So whatever is sitting there is what, because we're supposed to have an x, is what I usually say let u to be what is sitting there, which is f of x. In this case I have a y. And then to find the derivative of this whole thing, I'm going to have a 1 there, and I'm going to say that, oh, okay, this one I'm still going to have d dx, but here this is the same as a to the power y, a to the power u, because my y is just a u there. And then if you look into this particular case, this x and that u, they actually are not matching. So I wanted to end up taking the derivative of this with respect to u instead. So I'm going to say I want the derivative with respect to u instead of a to the power u. But I did not have this thing here, so I end up having to take the derivative of it again with respect to x, which is what was there. This one is still there. And then, of course, here, I know that 1 is there. And then here, what is the derivative? I have a u and a u. I know the derivative of this is going to be the same thing as a to the power u times ln of that constant, which is a there. And then, secondly, this one here is still going to be du dx. Why am I going to leave this u here? Because u is the same as y, and y is f of x, and I don't know what is y in terms of x. So I have this nice thing here as it is. So I end up saying that actually I can say that I can divide on both sides by a to the power u on both sides. So I will end up having 1 divided by a to the power u, and then ln of a is supposed to be equal to du dx, or du with respect to x is the same as 1 divided by a to the power u ln of a. So now what was my u? My u was actually y. So here I actually have dy dx here, which is just the same as 1 over a to the power y. Here I have my y there, and then I have my ln of a. And then this one here, dy dx, I mean, this is just the same as f prime of x. I know that thing. And then I have 1 divided by a, but my y, if you go back here and look at what was happening, my y is the same as log a of x. So that was my y here. So here I end up having log a of x, because y is log a of x, and then I have ln of a, which means now my f prime of x is simply 1 divided, I have log a and a, which means I'm going to just have an x which was inside, because this and that cancels out, and then I'm left with ln of a. So what this simply thing mean? It means that whenever I have the derivative with respect to x of log base a of x, this is always going to be equal to 1 divided by x times ln of a. Again, another thing will be, now if I change this base to be e, in other words, if I am looking for the derivative with respect to x of log base e of x, I am going to get something like 1 divided by x times ln of e, because now instead of a I have an e, so I will end up having something like this, which means now, because this is just ln, and you can see that is 1 over ln of e. We know that it is 1 because it's log e base e of e, so it's going to be 1. So this is just 1 over x. So the derivative with respect to x of log base a of x, we know that it is always going to be equal to 1 over x times ln of a, and the derivative with respect to x of ln of x is always going to be 1 over x. That's what I want you to understand, and we have answered 2 of the questions I think we had up there. Now we had also d was saying we have f of x, and f of x was equal to log base 2 of x. So what was f prime of x? Of course, it's going to be 1 divided by x times ln of base 2. That's simple as that, because that's what we're actually doing here. We take the base as it is and we plug it inside ln. That's the derivative of that function. And the last one, which was e, we're saying that we have we had y is equal to log base e of x squared and then plus y squared here. So what I want you to notice here was something that is interesting, that this is actually a function f of x, and also this one here now is going to be an f of x and then it is squared here. So the first thing that you have to notice here is that I know how to take the derivative of f of x when I have log base a of x, or because here we are having an e. This actually, let me just rewrite it, it's just ln of x squared plus y squared, and I know how to find the derivative of a function that is ln of x, because the derivative of this function is going to be 1 over x. That's it. But now, instead of having an x here, I have something, so I'm going to let my u to be what is inside there. So my u is going to be actually x squared plus y squared. And my v now, the reason I'm not using y, because we've been using y throughout, this y here, the y is already part of this equation. So my v now, which is actually the new function here, is going to be, I'm focusing on this here, so it's going to be equal to ln of, I'm replacing this thing by u, so I have a u there. It's going to be ln u. So dy dx, so dy dx is the derivative of this thing here. Instead of having f prime of x, because we're given y, so I'm using dy dx, is supposed to be equal to, but now I'm going to take this one here for the right hand side, so I'm going to have dv, but now because this is in terms of u, so I'm going to take the derivative with respect to u. But now we did not actually have a u there, that is why I have to take that u out, but now I have to take the derivative of u with respect to x. Now this is going to be so easy. I have my dy with respect to x, and then I have du, and then instead of v, I'm going to have ln of u, and then this one here I'm still going to have dx, and then instead of u, I'm going to have x squared plus y squared. And then secondly, I'm still gonna keep dy dx, and then here I know how to take the derivative. If this one and this one is the same, I know that it's going to be 1 divided by what is inside, so we have a u there, times dx of x squared plus y squared. Now I have my dy dx on the left hand side. On the right, I end up having 1 over u times the derivative of this thing here is just going to be 2 times x plus the derivative with respect to x of y squared. Right. Now let me do something here. I'm going to replace, I have this dy dx, 1 over what was actually u. Let me go back here. My u was x squared plus y squared. My u was x squared plus y squared. And then inside here, I have my 2x plus dx of y squared. Yeah. If you look into this here, this y here is actually a function f of x. So I have a function that is sitting inside here. So that function here, I am actually going to just say, let my u, take note that this u now is a new u, it's not the same as the one that we had above. So we have a u which is equal to a y here. So this whole thing is going to say dy dx is going to be equal to 1 over x squared plus y squared, and then inside I will end up having 2x plus dx of u squared. And if you look into this, the left hand side is still going to be dy dx, and then on the right hand side I will end up having x squared plus y squared. And then if you look on the inside here, I still have that 2x, and then this one here, I have a u inside and I have an x. I can't take the derivative of u with respect to x. That is why now I have to take the derivative with respect to u first of this u squared. But this u was not part of this, so I needed to take the derivative of this u, new u, with respect to x to encounter what I did here. So that is why now we end up having something nice as dy dx is equal to 1 over x squared plus y squared. And then inside here I'm still going to have 2x plus the derivative of this with respect to x is going to be something that is so nice, nice as u and u. So I'm going to end up having 2u here, and then times du with respect to x. At least now everything is actually working in order. And then secondly, we're actually having dy dx is actually equal to 1 over x squared plus y squared, and then I have this 2x here plus 2. What was my u? The new u here was actually y, so this one here is just going to be y, and then d, this u here is actually y, and then I actually have dx here. So I have this dy dx, I have that dy dx. I wanted to both of them to be on one side. So in order for me to actually deal with that, I'm going to multiply this to that side. So I will end up having, I'm going to cross multiply this. I will end up having x squared plus y squared times dy dx must be equal to 2x plus 2y dy dx. And if you take note of this, I'm going to take this to the other side and its sign is going to change. I'm going to leave this here. So I end up having x squared plus y squared dy dx, and then minus 2y dy dx is going to be the same as 2x, because 2x is going to be left alone there. And then after that I factor out dy dx, and inside I will end up having x squared plus y squared if I take this one out, and then if I take this one out I'll be left with a minus 2y, and then on the right hand side I end up having a 2x there. And then of course if I divide by this on both sides, I end up with the dy dx being equal to 2x all over x squared plus y squared minus 2y. You can see how easy this thing is, because that's actually what we were looking for, because we're given something nice as this. So this derivative is actually going to be 2x divided by that, or in other words, the slope of the tangent line that is touching the curve y is equal to log e of x squared plus y squared, is just given by this function here. Just a quick recap, you take the derivative of that, which is going to be dy dx, and then you take the derivative of this. You know that because this is ln, so ln is going to be 1 over whatever is inside there, which is going to be x squared plus y squared, and then you take the derivative of the inside, and the derivative of this is just going to be 2x, and the derivative of this, you bring the 2 down, and then after that we take the derivative of this with respect to y, so you end up having a y, and then you take the derivative of this y now, because this is a function with respect to x. So to back to x, and then after that you just simplify. You want this to go with that, you play with algebra, you will end up with that. So that's how easy this thing is. Or you can go by following what I was just doing, but this is also another shortcut. Take the derivative of the inside, but you must know that this is a function, so there must be a dy dx that is coming out of this y. There must be dy dx that is coming out of this y, and that's where we will actually, and hopefully you enjoyed this particular lesson. And these are some of the nice things. They are hard when you're actually doing them for the first time, but the more you keep practicing, they become easy and easy, and you actually started to like working with them. So I'm actually going to end here, and then we'll see you when we're actually doing the another lesson, which is we can either have a bunch of derivative problems, or we can go straight to higher order derivatives and see what we can actually get, and see if we can actually understand this whole thing. Thank you.